Okay.
Let's see. I actually took pretty good notes today.
Okay. Well, let's choose your next prompts, and we'll start slow. So today we're taking KC first. So
Right, KC was concentration.
So, oh, okay, 4%, right? So can you tell me what equilibrium is? Just so that I know.
Just balance between both sides of the equation.
I know what you're trying to say, but be careful with that because balance just means moles, right? That means like stoichiometrically. But
right.
Equilibrium is talking in terms of kinetics, actually.
Okay.
So equilibrium means that the rate of the forward reaction is equal to the rate of the backward reaction. So the concentration isn't changing at equilibrium, right? Because the forward and the forward reaction and the reverse reaction are happening at the same rate. So everything's stable. Okay. So for this one, I'm going to give you a couple compounds, a couple gas compounds.
Okay.
And we're going to work out how to form them. Like we're going to write the equation for how you would make them, and then we're going to talk about the equilibrium. So the first one's HF. What's HF? Yeah, and this is gaseous hydrofluoric acid. So we're going to make this. We need two elements to make this. Which ones would those be?
Hydrogen and fluorine.
Yes. Okay. So what's hydrogen in its gaseous state? What's the formula for gas?
H+.
That's the hydrogen ion, but we need H in its gaseous state. Like you referred, like think about like a balloon. Like they shouldn't go up. Hydrogen. Yeah. Perfect. So we need H2.
Plus, and then would F2 be F2?
Yes.
Yes. And then it goes into equilibrium.
Okay. So is this balanced?
Now you need two HF on the right side.
Yeah. Or you could do a half mole of each of these. Whatever. So now you have this. So KC would be
HF, concentration of HF squared over concentration of H2. Concentration of H2 multiplied by concentration of F2.
Yeah, good. Good. Okay, so that makes sense. That's pretty simple, right?
Yeah. I mean, it gets weirder when you have like KC and KB and KA and KW.
Well, why don't you tell me what those are?
Well, Ka has to do with the acid, and so that is when you have an acid plus water, or an acid.
No, that's right. Acid plus water. Can you give me an example of like a reaction you find the Ka for? Actually, why don't we just do one of those?
Yeah, because
a lot of stuff here. Let me find the right one I want to do. Okay, so you need to use Ka for this problem, even though we're not finding Ka technically.
okay.
So we're going to find the pH of a 0.100 molar solution of acetic acid. And they're going to give us that the Ka equals 1.8 times 10 to the negative 10. So where do I set?
An ice table.
An ice table. And what do we need for the ice table?
Formula.
Okay, good. What's acetic acid? Do you know?
Not by heart, no.
Okay.
HCOOC2OH.
Wait. So what did you say?
HC2OH.
HC2.
H2COH?
H2COH. Yeah, actually.
The second one, right?
Yeah.
Yeah. Okay.
Yeah, I mean CH. Oh wait, no, actually, you're close. It's CH3COOH.
Okay.
You're close. CH3COOH. You'll.
I don't know what I said. I mean, I don't know what I went.
You left out.
The C.
Well, hydrogen. Yeah.
I left mine.
You're close. That's okay. So then, what's this gonna go with? It's an acetic acid solution. So that's acetic acid and
Water.
water. And this is a weak acid, so we know it's gonna go backwards. So what's that gonna go to?
Well, first we'll do CH3CO minus.
Right, that's called the acetate ion. Plus
hydronium.
hydronium, yeah, really good. So which one of these is the conjugate base and which one of these is the conjugate acid?
The conjugate acid. Okay, so acetic acid, the conjugate base is the acidic, whatever you call it, I forgot already.
This one?
It goes acid, base, base, acid.
Yeah, but just so that like we actually know what it is, that's out of order.
What is it called?
So the acid is on this side.
Right.
And that goes to the conjugate base.
Right.
Because this would be the acid, but it's the acid deprotonated, which is a base. Right?
Right.
So acid, conjugate base, base, conjugate acid. You see why? Because it's the acid-base versions of each other.
Mhm.
Okay, so I said we have a 0.1 molar solution of this. So what's our initial concentration?
0.100 molar. And then we don't worry about water.
Yeah, we don't need to worry about water because it's a pure substance. It's a pure liquid. So what's our change? Oh, yeah, and then for these two.
0 and 0.
Good.
So then you have minus x on the left-hand side and then 2 plus x's on the right-hand side.
So for each quantity, we're adding x?
Yes.
Yeah.
Because they're each 1 mole in the original mixes.
Yeah, you already know where this is going. You're a pro. 0, 0 minus x. So then over here, this is just going to be
X and x.
x, yeah. So then how do you want to solve this?
X squared over 0.100 minus x equals 1.8 times 10 to the negative 10.
Good. Okay, so we could solve this with the quadratic, but do you know about making the assumption?
Yes.
Okay.
The assumption that I never know when I'm supposed to make it or not.
I think it kind of depends. I've heard different like rules of thumb. I've
We
heard
didn't do
like
this in class today.
yeah. I think he's going to talk about because you guys. This is like half the class.
Yeah.
Stuff. So I think he'll get to it later. What I've heard is that like if once you eventually go back and solve for it, like if x is less than 5% of the quantity you're subtracting from, then the assumption is valid. But
Didn't it have something to do with like the size of K? Like if K compared to the
the
molar concentration, like there was like some sort of thing in the book that they talked about that I can't remember.
Yeah, off the top of my head, I don't remember, but for this problem, you'll see that they go with something for this problem.
Because it's a -5, it's really small, so we can kind of just assume that x is going to be really small.
So yeah, let's assume. So then x squared is going to be 0.100 times 1.8 times 10 to the -5. Do you calculate already?
Yeah.
Actually, I'll just tell you.
Okay, that's fine. I should probably look for my calculator anyway. I always feel paranoid that I'm going to lose it.
That's 1.8 times 10 to the -6. So then we square both sides, right? Square root, and we get Okay, so before I take the numbers, what's the quantity we're getting? Can we solve for x? What actually is that?
It's just the difference between the original molar concentration and the equilibrium concentration.
Yeah, that's true, but that is something. Think about the chemistry now, not the math. What is x?
The amount that's getting converted to the base. The amount of acids being converted to base.
Yeah, I guess that's true, but what I'm really looking for is that's the concentration of hydronium, right? It's concentration of H2O+.
Oh, yeah.
Because then,
Because that's what we're trying to get to in this problem.
we're trying to find pH, right? So this is going to be equal to the concentration of H3O plus, which is equal to the concentration of OH-. So you're right, it is technically the amount, I mean, in this problem it's CH3OO-, but yeah, it's the amount of acid and the amount of base. So you are right, but this is what I was looking for, because you got to remember, pH, I should give you, this is 1.3 times 10 to the negative third.
Because we took the square root.
Yeah.
How did it
So,
end up being 1.3 if it was 1.8?
I don't know, maybe I plugged it in wrong.
Yeah, you have 1.6 on your paper because it's 1.8. Or it was originally 1.8. It doesn't really matter.
Let me see if I can do this. Yeah, I don't have my calculator. Let me Google it.
No, I got my calculator.
Oh, okay, can you do it for me? Actually. Nope, that's not right.
I got 4.2 times 10 to the negative 3.
So 1.8 times 10 to the negative 6, and you take the square root of that. you get-
Well, then 1.3 times, yeah. Yeah, it is 1.3 times 10 to the negative 3.
Okay, good stuff. So now that we get that, what's the formula for pH?
Negative log that.
Negative log of concentration of H2O plus.
2.87. H is 2.87.
Yeah, my God. Yeah, the actual value is 2.8. Like, if you plug in with the pH meter, it should be about 2.8.
And what about significant figures on that?
Let's see, how many
We
stick figures did I have? 3? So it'd
No,
be
2 on the KC,
case.
right? 1.8?
Yeah, I had 2, so it'd be 2.9 would be the right answer.
Yeah.
Good catch. Okay, so I feel like you have those problems pretty much down.
Yeah.
You want to talk about some theory stuff? You want to? Oh yeah, let's go through strong acids and strong bases.
Okay.
So what's a strong acid versus what's like strong versus weak?
Well, strong acid dissociates completely in water.
Yes. Okay, that's true. So
And
if I was-
also, is a strong acid has a lower pH.
Yes. I'm trying to
Not
think.
where you're going at all.
Well, no, I'm just trying to think if that's an always. You know what I mean? I'm trying to think.
Well, like if it has a pH of 1, it's a strong acid.
Yeah, but the pH is dependent on the concentration, right? pH is negative log concentration of hydronium. So if you have a drop of hydrochloric acid in a liter of
So even though it's
water.
got a low pH, a high pH, it's still a strong acid. It's HCl.
Well, remember, pH isn't an inherent property of acid, right? pH is a measure of how much acid you have. And so if you have a certain amount of a strong acid, you're going to get the most bang for your buck compared to a weak acid. Because if you have an amount of a weak acid, you have to calculate how much acid you're actually getting in your solution. But if you have a strong acid, you can assume that pretty much 100% of it is going. So it's fair to say that, like, in terms of pH, strong acids are like more efficient.
Mhm.
But if you have really concentrated vinegar,
that's acetic acid. It's a weak acid. That's probably still has a higher pH than like super dilute HCl.
Interesting.
Yeah, because it's concentrated.
It makes sense, but I never thought of it that way before.
Yeah, so pH is a measure of that, but don't think about pH as like an inherent property. So yes, that's right. So this is kind of a nitpicky detail, but would it be a forward arrow or would it be a forward back arrow for strong stuff?
Forward only.
Forward only, because we're assuming it's dissociating 100%. So what about weak stuff?
Then it has both forward and a back arrow.
Yeah, because it's not going to be dissociating completely, so you're going to have both, and it'll be reforming. Yeah, good stuff. Can you name any of the strong and weak acids and bases? You guys didn't today.
Yeah, I didn't memorize them though.
That's something I would totally memorize. I would flashcard that to oblivion, just because there's going to be so many problems. I remember when I took this class, I didn't have them memorized, and we had quiz, and I spent so long working on it, like right up until the bell. We turned it in because I was trying to do an ice table and calculate it, and I realized like, oh, this is a strong acid. So that's something that can save you so much, especially like learning how to do the assumptions correctly too. Those are good things to practice because that'll just save you time. That'll just save you a lot of time, and that's gold in this class.
Yeah, I don't know. I totally messed up last semester.
It happens. Everybody does. Okay. Do you have it written down?
Yeah.
Oh.
HCl.
Yeah.
HBr.
If you don't know, I write the names too, just for.
HI. I don't know them all. Hydrochloric acid.
Hydrochloric, hydrobromic. I think HI is actually just iodic acid. I don't think it's hydroiodic acid. I don't remember.
Who knows?
Yeah. HNO3 is. Remember?
I wrote that one down. Nitric acid.
Nitric. And then perchloric and sulfuric.
Okay, so there's 6 strong acids.
And 8 strong bases.
And that's it. There's no more secret ones that I need to know about.
No, I don't think so.
Okay.
Don't quote me on that, but no, I'm pretty sure that that's all you need to know. Why? Do you know HF isn't one?
Why?
Yeah. Did that bug you that HF isn't one?
A little bit, yeah.
So I don't totally remember, but I was thinking about this. I'm pretty sure that has to do with size, because fluorine size decreases while electronegativity increases. You remember that?
From
Chem 1.
From Chem 1, yeah. I like I said, I took Chem 1 last year, so.
Okay, well, how about this? So let's say this is the periodic table. This is the periodic table. And
excellent.
Electronegativity is going to go this way, right?
Yeah.
Electronegativity. Well, this is size. The red is size, so it's opposite.
Oh, it's exactly opposite.
Yeah. You remember why?
Because so if you're more electronegative, you're like more attracted to the center.
Yeah. So more electronegatives are pulling the hydrogen clouds closer to the nucleus. Yeah. So where's hydrogen?
Hydrogen is all
And where's fluorine?
all the way up there.
I'm pretty sure it's because hydrogen is so much bigger than fluorine.
That it just like engulfs it.
It doesn't engulf it, but there's something going on, and I don't totally remember what, but that has something to do with size. I believe. I'll look it up at some point. Another good rule of thumb is that, so you probably know this, but yeah, for acids, you're going to see H and then something that's like obviously a negative ion. Whereas for strong bases, you're going to see an OH, which is like with one of the alkali earth metals or alkali metals. Lithium, rubidium, calcium, potassium, magnesium.
What are you getting at? I don't get what you're getting at.
So if you see like something with like the alkaline earth metals or the alkaline metals with the hydroxide, that's a tip off that it's a strong base.
Oh, okay.
Like lithium hydroxide, sodium hydroxide, potassium, rubidium, cesium, calcium, barium, strontium. Those are all on the far left side of the periodic table, right?
Yeah.
Yeah. So that with hydroxide is a tip off that it's a strong base.
Okay, that actually just covers every single strong base that he said in class.
Yeah, because those are strong bases.
And they all come with an OH or a hydroxide.
Yeah.
Or two.
Or strontium, calcium, and barium. Yes.
It's like
Yes.
something back here. I know you're right.
Uh,
See, what else do I have in here?
Here's just kind of a cool question that I like actually. Okay, so you have this reaction, right? It's 2SO2 gas plus O2 gas. It's going to go to 2SO3 gas. Okay, that's a plus. We want to figure out how to increase the SO3 to SO2 mole ratio. There's a couple
That's
ways.
an interesting question.
Yeah, there's a couple ways we could do. So we want to optimize the products, basically. We could add a catalyst. We could drop the temperature. We could take out O2 and remove some of the O2 gas, or we could drop the pressure.
Drop the pressure.
Drop the pressure, why?
Because that's the one that changes the mole ratio.
I left out one clue, I'm so sorry. There's one vital clue, and that is that the delta H of this reaction, delta H is negative 198 kilojoules. Does that change your answer?
So that would put it on the right-hand side, so no, that doesn't change my answer. I'm still gonna stick with it.
Okay, so if we drop the pressure, Le Chatelier's principle is going to favor the side with more gas molecules.
Oh, so that's not gonna make it.
So that will make the denominator bigger. So that's going to push towards the reactant side.
So that does do something, it doesn't do what we want.
It does do something, but that's going to push towards the reactants. We want to push the products. We want to optimize this. We want to get the most SO3 gas that we can. So lower pressure is not going to work. How about adding a catalyst?
We're not gonna get any more, it's just gonna go faster.
Good. What if we take out O2?
Take out O2, then how would you make the SO2?
I mean, let's say we have some of it and we vacuum. We have excess.
We're
Right?
just lowering.
How about we have excess?
That doesn't change the mole ratio. No, I'm down. I mean, it's gotta be the temperature, and that's why you're like, this is a crucial piece of information.
Yes, it is, but let's be.
But I don't
let's be
see
analytical.
it, I don't see it, I don't see why that works.
Okay, so remember what he said today about thinking about energy as a product? If this whole reaction is negative, where's the energy? It's on the product, right? We take out some of the product, which
Then
way
you're
does
gonna,
it go?
then it's gonna
It's going to
fill
shift to the right. And if we lower the temperature, we lower the average kinetic energy. So we drop the temperature, we drop the enthalpy.
Okay,
Make sense?
yeah, I hope that's one of the questions.
I don't know. I pull a lot of these from the ACS review guide just because I always tell people to go look at that. Oh, yeah, these are from there actually, a lot of them. 'Cause I always tell people to go look at it, and I know they never do, so I just do some problems.
Yeah, I have that thing, and I studied it for the final exam in Chem 1. I got an A in Chem 1, but
there
I
you
did
go.
not do well in Chem 2.
Good stuff. Let me see. I feel like you're good on the problem solving, so let's do more. Actually, also, let's make sure you're not late to the thing.
No, it's not
Okay.
for freaking 15 minutes.
Let's do more theory, because I feel like your math is fine. So let's just make sure like the chemistry is solid. Let's talk about the difference between acid classifications.
Between strong and weak?
Arrhenius, Bronsted, and Lowry, and Lewis.
Oh, well, I
if you know
have it
this.
literally right in front of me.
Well, don't look at it.
Okay. Arrhenius is, if it's an acid, it
Don't look, don't do it.
it has something to do with hydrogen, producing hydrogen versus producing hydroxide ions. So base, I feel like produce is the wrong word, but it has to do with, it has a higher concentration of hydroxide ion versus like being a proton donor or proton acceptor, which is Bronsted already.
So you're on the right track. So an Arrhenius acid is just something that like has H plus, right? And so then Bronsted Lowry changed it to say that an acid donates H plus, and a base accepts it.
Right.
Did you guys talk about Lewis?
No, I mean, last semester we did, but, I mean, when I was taking it last semester.
Yeah, okay. Well, do you remember the Lewis definition? We won't do anything with Lewis because you don't need it yet, but do you remember what Lewis is?
No.
Okay. Well, a Lewis acid is going to accept electrons.
Electrons. And a base will donate electrons.
Yeah, good. Good. So that's like, you can do, okay, cool. So I used to do research. I used to do synthetic chem research in a lab here. So we would have this compound. So we would have an amine group here. Oh, sorry, NH3. We would have ammonia, but it's bonded to something. So nitrogen has 4 bonds, which makes it positive, right?
Mhm.
So that looks like this. NH. So this is acidic, right? So what we could do is react this with something called triethylamine. Triethylamine is nitrogen with these. These are 2 carbon chains coming off it. But this says it's lone pair base here, 1 pair. So this is going to be a good Lewis base. This, grab this guy, and then these electrons from the bond go back here. So then that's going to give us an H2OH plus but so did you see what happened here? The base
Donated electrons.
donated these electrons to get the hydrogen, and then the acid accepted the hydrogen back from that bond. See that?
Yep.
That's Lewis, which you'll see a whole bunch when you take organic.
Okay.
That's organic chemistry.
Yeah, it looks like very organic.
That kind of makes sense?
Mhm.
Okay. Let's see. I'm trying to think if there's anything else that's like a highlight from today that's big. Did you guys do the darker mixture problem? Like there's something at equilibrium that it gets darker, you need to figure out if it's exothermic and which chemical. Okay, oh, this is kind of cool then too. I'm hopping all over the place, but so we have 2NO2 gas goes to N2O4 gas. And so it gets darker when it's high temperature or low pressure.
Okay.
And so we want to figure out which chemical is darker and if this is exothermic or endothermic.
Okay.
Okay.
So we don't know, so it gets darker when there's a low pressure.
What happens when there's low pressure?
It favors the side with something moles.
You got it.
It's gonna favor one side. Less moles or more moles?
Normal.
More moles, there you go.
So lower
Lower pressure.
favors the side with more moles.
Yeah, you got it. So which side is gonna be favored?
The left.
Mm-hmm. So that's gonna tell us that NO2 is darker, right?
Right.
So now we need to figure out if it's exothermic or endothermic. So it gets darker at high temperatures. What does that tell you?
It is exothermic.
It is exothermic. Why?
Well, if we're thinking of the temperature or the kilojoules as a product, it would have to be on the right-hand side in order for it to get darker without higher temperatures.
Yeah, really good.
I learned from that other problem you gave me.
Yeah, really, really good. These were the hardest problems when I was in class, just like thinking about the chemistry side of it. But the biggest like tip I ever learned in a chemistry class was that like the math is easy, but like the chemistry is really hard. So if you can kind of work problems like that and focus on like what's going on with the chemistry, then the math comes really easily. It's like, oh, well, this has to go that way because this is how chemistry works.
Yeah.
That's always the best tip I give people. Like I took a class on analytical chemistry, and it's basically this. Basically just like titrations and acids and base all over for a whole semester, but to like solve problems like that. And the math was really easy, but it was a hard class because it's algebra, and everyone here takes calc.
Right.
But chemistry is hard to figure out, so that's the hard part.
Okay, low pressure favors more moles.
Yeah.
So I just have to remember that low is not less. That's gonna be really confusing.
Yeah, I try to never come up with those like,
I always
because I always
do it, though.
confuse myself with them.
Well, I did some pretty good work in physics doing that.
Mm-hmm.
I was doing some stupid whatever.
Are you in physics 1?
Yeah.
Good stuff. But that's a fun class though, mechanics.
Yeah.
It's a trig. Almost a
Yeah, lots of trig.
trig. Have you taken calc yet?
Yeah, I took Calc 1 and 2.
Okay, so you know like the differentiation, integration of like velocity and acceleration. That makes the class so much easier. I didn't know that when I took it.
Oh, really?
No,
You took physics without taking Calc?
I took Calc 1 over a whole year instead of a semester. And so the time when I was taking physics, I didn't know that yet until like the end of the class. And I was just like, what? I didn't need to know any of these equations. Yeah, it was a good time.
Yeah, no, I hate that class. I hate calculus classes, but it's okay.
It's okay, you'll get in med school. What kind of doctor do you want to be?
Psychiatrist.
Oh, good for you. That is a tough job. That's oftentimes a very thankless job too.
Mm-hmm.
But good for you.
Yeah, I'm pretty excited about med school. I just need to stay in Chicago, which is the hard part.
Well, the good thing is we have tons of medical schools here.
Yeah, so I have like a good chance of staying in Chicago, but still stressful thinking about that whole process of applying and everything.
Yeah, I get that.
Yeah, aren't you taking the MCAT at the end of this year?
Oh no, I'm gonna take it at the end of my 5th year.
Oh, so you're not even gonna take it for like 3 years.
No, but it's still 2 years from now I'll be taking it. Still stressful.
Yeah.
I want to be a pediatrician.
Oh, well, I want to be a pediatric psychiatrist.
There you go. Yeah, I want to be
That's a really cool connection.
some type of pediatric specialist. I
Yeah,
love kids.
yeah, definitely. That's a big motivator for me. I have a stepson.
Okay.
He's 11.
Good.
I test out my themes on him.
I'm very jealous. Take care. Happy Valentine's Day.
See ya next week. probably.
See you on Thursday.
No.
Can I go to class?
No, isn't it 8 to 9 on Thursday? I go.
Oh yeah, but I'll be in class.
Oh.
I'll be in your lecture. I have to go to those.
Well, then, yeah.
Take care.
Bye.
Okay, I don't know if anyone's listening, but nobody's here now, so goodbye.